December 1943. The English Channel rolls under a cold, colorless dawn, its surface shifting like hammered steel beneath a rising wind. In the half-light, the silhouette of a tank emerges from the mist, its engine grumbling, its treads clattering softly. But it is not on land. The machine advances across a narrow road that should not exist, a slender line of metal floating on black water. Each swell lifts the structure, each trough drops it again, yet the roadway holds steady, rising and falling with a strange, deliberate grace. Behind it, trucks, fuel carriers, and armored vehicles wait patiently for their turn, engines rumbling in the uncertain gray of morning. A handful of engineers stand on the deck of a nearby vessel, watching the demonstration with tense concentration. Among them is a young Royal Engineer, Major Allan Beckett, quiet and almost invisible beside the senior officers. He watches the tank climb the floating track toward a distant beach, a faint expression on his face, half relief, half disbelief, because he knows what no one else does. If this fragile road across the sea works here, in controlled conditions, it might work in war. It might carry the weight of an entire invasion. And to understand why such a road had to be built at all, we must return to the world that demanded it. War had reshaped Europe long before anyone imagined driving tanks across floating roads. The First World War had already shown the terrible cost of attacking fortified shores, and no one carried that memory more heavily than Winston Churchill. In 1915, at Gallipoli, Allied troops had been thrown against steep cliffs and prepared defenses without the support of proper landing infrastructure. Men drowned under fire, boats splintered at the waterline, and months of costly fighting yielded nothing but grief. Churchill resigned in disgrace, the weight of that failure shadowing him for decades. When the Second World War erupted, the ghost of Gallipoli returned, not only as a political scar, but as a lesson carved in blood. Never again would an Allied force assault a defended coast without the means to sustain itself. Logistics, not heroism alone, would determine victory. By 1940, that lesson had grown urgent. As British soldiers retreated to Dunkirk, the entire army seemed in danger of being swallowed by the sea. The improvised evacuation, carried out with fishing boats and pleasure craft, rescued hundreds of thousands, but at a terrible cost in equipment and confidence. Britain had survived, but only barely. And as Hitler tightened his grip on continental Europe, it became clear that one day the Allies would have to return, somehow, somewhere, to the shores they had been forced to abandon. That return would demand not a quick raid but a full-scale invasion. The storm-tossed channel, barely 20 miles wide, might as well have been an ocean unless the Allies could find a way to cross it with overwhelming strength and sustain that strength for weeks, even months. By 1942, planners studying the coast of northern France reached a grim conclusion. No deep-water port could be seized intact. Every major harbor that could support a modern army, Cherbourg, Le Havre, Boulogne, Calais, was fortified, mined, surrounded by concrete, and expected to be demolished the moment Allied troops approached. Even if a port could be captured within the first days, the Germans would certainly destroy cranes, quays, storage areas, and anything else vital for unloading ships. Without a port, the invasion risked stalling on the beaches as precious supplies piled up offshore aboard ships that had nowhere to unload. The Allies could win a beachhead but lose the campaign. Logistics would decide the fate of the entire Western Front. Churchill understood this with painful clarity. On May 30, 1942, he sent a brief but electrifying memo to the chiefs of staff. It contained only a few words, almost casual in tone: Piers for use on beaches. Those 4 words set in motion one of the most ambitious engineering efforts of the war. The piers must float, he wrote. They must rise and fall with the tide. They must allow heavy vehicles, tanks, trucks, artillery, to drive directly from ship to shore. And above all, they must be ready before the invasion began. Churchill was asking for something that seemed to defy engineering logic: a man-made port constructed not near the water, but directly in the open sea. What followed was a collision of imagination, urgency, and bureaucratic disbelief. The Admiralty doubted the idea entirely. The War Office struggled to interpret Churchill's direction. Different groups proposed radically different concepts: giant concrete platforms, floating mats, steel pontoons, collapsible causeways. Some designs looked too fragile. Others were impossibly heavy. Many seemed unworkable in the violent tides and storms of the channel. Yet the need was absolute. If the Allies could not create a harbor where none existed, the invasion of France, the most complex amphibious operation in history, might be logistically impossible. Into this atmosphere of pressure and experimentation came a 28-year-old Royal Engineer named Allan Beckett. A civil engineer by training and an experienced small boat sailor in peacetime, he had the kind of intuition the project desperately required, a practical understanding of how structures behave under stress and how the sea itself behaves when challenged. When a War Office officer handed him a secret sketch describing Churchill's idea of a floating pier, simple lines on paper, lacking detail but filled with expectation, Beckett studied it quietly, absorbing the enormity of the task. The idea was not only bold, it was unprecedented. A mile-long road that hovered on water, carrying the heaviest vehicles in modern warfare, and surviving storms that tore apart steel-hulled ships. But Beckett's mind did not recoil from the impossible. He began searching for a solution not by imagining rigid strength, but by imagining balance. Waves could not be defeated. They had to be worked with. A floating road had to move, not fight. It had to bend, not break. And as Beckett began drafting the first forms of the structure that would later be known as the WWII, he understood that solving Churchill's challenge meant more than building a bridge. It meant rethinking how an army touches land. And that challenge would soon lead him into experiments, prototypes, and a competition that would decide the final shape of the floating road. Allan Beckett's first sketches revealed a mind working in several dimensions at once. He understood instinctively that any structure built for the channel had to accommodate the sea's will, not resist it. Traditional military bridging relied on rigid spans, precise angles, fixed supports, but the channel was a living force. It rose and fell by several meters each day. It twisted the hulls of ships, tore apart moorings, and hammered anything that dared stand still. To build a road that floated, Beckett believed, required a structure that behaved like a living thing, flexible, mobile, and strong only where it needed to be. So he began drafting a span composed of hollow steel box girders arranged in a distinctive lozenge shape. This pattern allowed the span to twist slightly when waves passed under it, distributing stress instead of concentrating it. Hinged joints at each end allowed controlled motion in 3 directions: pitch, roll, and yaw. This would be no rigid dockyard pier. It would be a chain of interlinked steel vertebrae, what the engineers would soon call a whale. Yet a floating road is nothing without buoyancy. Beneath each span Beckett imagined a pontoon, essential, stable, and rugged enough to withstand months of channel weather. These pontoons, soon nicknamed Beetles, would support the weight of the spans and absorb the energy of the waves. Some were built of reinforced concrete, others of steel, but all shared a simple principle: they must lift the roadway with calm reliability, no matter the sea state. The spans and pontoons together formed a dynamic system, one that moved with the water rather than against it. But ideas were only the beginning. The War Office needed proof. To test the competing designs, officials chose a remote stretch of coastline in southern Scotland, Garleyston, in Wigtown Bay, whose tides mirrored those of northern France. Its seclusion offered secrecy, its waters offered truth. There, through late 1942 and into 1943, engineers erected prototypes along the shore. Beckett's flexible whales faced rivals: a concrete roadway system known as the hippo and crocodile, and a vast textile-based floating mat called the Swiss roll. Each concept embodied a different philosophy of amphibious logistics. The tests became a quiet, high-stakes competition, watched by senior officers who understood that the future of the invasion might hinge on what survived the Scottish winter. Storms soon swept the bay. Waves slammed into the experimental structures, lifting and twisting them with unforgiving violence. Observers held their breath. On rough days, officers saw the concrete roadway fracture under stress. They saw the textile roll twist itself into failure as waves overwhelmed its design. When the winds finally calmed, debris washed ashore in long, tangled sections, a silent verdict on their limitations. But the whale remained. Beckett's spans had flexed with the waves, not shattered under them. The Beetle pontoons had risen and fallen without losing rhythm. The prototype had endured precisely because it had been built to move. The choice became clear. In London, planners authorized production on a scale rarely seen for an engineering device. Thousands of workers across Britain, steelworkers, welders, riveters, machinists, contributed to the manufacture of the spans and pontoons that would become the backbone of the Mulberry harbors. In quiet workshops, teams cut steel into exacting patterns. In coastal yards, pontoons took shape like silent fleets waiting for their moment. Every piece was destined for one purpose: to help the Allied armies land and remain in France. But even with a flexible roadway and reliable pontoons, a critical danger remained. The sea does not merely lift structures, it drags them. A floating road anchored improperly becomes a weapon against itself, a vast lever that can wrench free and tear apart everything attached to it. Traditional anchors were either too light to hold or too heavy to maneuver quickly. Without a breakthrough in securing the spans, the entire concept remained vulnerable. It was here, in the quiet margins of the project, that Beckett again made his mark. Drawing on his sailing experience, he began experimenting with anchor shapes in mudflats near the Erith Yacht Club. Off-duty and often alone, he dragged prototypes across the seabed, examining how they bit into silt and clay. Through trial and adjustment, he developed a design that resembled a swept, winged fluke, a form that dove deeper under strain instead of pulling free. This would become the Kite anchor, light enough for field use yet capable of holding tens of tons against the shifting power of the sea. It was the final link in the system, the unseen foundation beneath every span. By early 1944, the pieces were ready. The whales, beetles, and kites, hundreds upon hundreds of them, waited in depots and assembly yards across Britain. Soon they would be towed across the channel, not as theoretical prototypes but as the arteries of a port that did not yet exist. The stage was set for one of the most daring logistical undertakings of the war. The story of the floating road is often told as an engineering triumph, but behind its steel framework lies a deeply human dimension. Allan Beckett was not the kind of figure usually placed at the forefront of wartime legend. He was quiet, thoughtful, and almost self-effacing, a man more comfortable with charts and drafting pencils than with speeches or spotlight. Yet within the Mulberry project, his presence became a steady, grounding force. Unlike many officers who approached problems through hierarchy or doctrine, Beckett approached them through observation, through the intimate knowledge of tides, currents, and the feel of a boat's hull under shifting winds. His colleagues later recalled him not as a boisterous innovator but as a patient solver of problems, someone who absorbed details others overlooked. The pressure on him was immense. He knew that failure would not simply mean wasted resources, it could cost lives in the opening phase of the invasion. Still, he worked without theatrics, focused entirely on the quiet craft of making something that would endure the sea's punishment. The floating road that would carry tanks into France began, in many ways, as the expression of one man's disciplined humility. To understand how extraordinary the Whale roadway was, one must picture its structure not as a simple bridge but as a carefully balanced mechanism. Each 80-foot span was composed of steel box girders arranged in a diamond-like pattern. This lozenge shape was not aesthetic, it spread stress across the frame, allowing the span to twist slightly as waves rolled beneath it. At each end were spherical bearings, ingenious joints that allowed controlled movement in multiple directions. Unlike rigid piers that fight the sea, the Whale flowed with it. Beneath the span sat the Beetle pontoons, square or rectangular floats that lifted the roadway like a chain of steady breaths. Some were concrete, built for durability, others were steel, lighter and more responsive. Together, these components formed a long, flexible chain capable of rising and falling several feet with each pulse of the tide. When assembled mile after mile, the structure became something remarkable, a floating highway strong enough to bear tanks yet supple enough to survive storms. It was an entirely new concept in amphibious logistics, a road that behaved like a vessel without ever being one. But a road that floats is only as strong as the forces that hold it in place, and in this, Beckett again confronted a problem no textbook could solve. The channel's seabed varied wildly from bay to bay. Sand, mud, gravel, and clay shifted with the seasons. Traditional anchors, whether Admiralty pattern or Danforth style, were designed for ships that could swing freely around their mooring points. The Mulberry roadways, by contrast, needed rigid positional stability. If a single span drifted, it could place enormous torsion on the entire network, threatening collapse. During the early design stages, some proposed using heavy concrete blocks. Others suggested burying massive deadweight anchors. But these solutions were impractical. They were too heavy, too unwieldy, and too slow to deploy during a time-sensitive operation. Beckett's answer came not from theory but from experience. He understood how a boat's anchor behaved when current increased, how certain shapes cut through mud until they found resistance. In tidal flats along the Thames, he tested small metal models by hand, dragging them and adjusting the angles until he found a form that dug deeper under strain. The result was the Kite anchor, a deceptively simple device shaped like a swept, tapered wing. Its geometry caused it to dive into the seabed when tension increased, locking itself more firmly as waves pulled against it. It weighed a fraction of the anchors used by the Royal Navy, yet its holding power exceeded 30 tons in ideal conditions. The Ministry of Supply quickly grasped its significance and ordered more than 2,000 of them. Ironically, the Navy dismissed the design for their own floating breakwaters, preferring larger, traditional anchors. Their skepticism would have consequences when the first Great Channel storm arrived after D-Day. But for the whale roadways, the Kite anchor became the unseen hero, small enough for engineers to handle quickly, strong enough to hold an entire harbor in place, and responsive enough to survive the unpredictable violence of the Normandy coast. These three angles, human, structural, and foundational, reveal a system far more intricate than its plain appearance suggested. The floating road was not a single invention but a fusion of insight, craft, and intuition. Beckett's capacity to recognize that flexibility could be stronger than rigidity, that motion could be harnessed rather than resisted, and that small solutions could anchor enormous structures, marked a philosophical shift in wartime engineering. His work did not roar like artillery or streak across the sky like a fighter plane. It moved quietly, bending with the tide. Yet it held the weight of armies. Ahead lay the operational realities of war, the need to transform this elegant system into a functioning port under hostile fire and unpredictable weather. And those realities would reveal entirely new dimensions of the floating road's significance. Beyond its technical brilliance, the floating road must also be understood as a weapon in its own right, a tool of strategy that reshaped the Allied approach to amphibious warfare. The planners of Operation Overlord knew that firepower alone could not win the campaign. Tanks, guns, and aircraft might secure the beaches, but it was tonnage, fuel, ammunition, rations, spare parts that would determine whether the invasion could push inland or collapse under its own weight. German intelligence expected the Allies to depend on capturing a port, or else to falter after a few days of beach supply. Mulberry shattered those assumptions. With its vast phoenix caissons, its floating piers, and its whale roadways stretching from sea to shore, it offered something unprecedented, a harbor conjured from open water, immune to pre-placed German demolitions. This artificial port would allow deep-draft cargo ships to unload directly onto floating pierheads, where vehicles could drive ashore in steady, deliberate flows. In a war defined by logistics, Mulberry was a quiet revolution, a weapon whose impact would be measured not in explosions but in thousands of tons landed each day. Without it, the Allies risked fighting the Normandy campaign with one hand tied behind their back. Yet the system was not uniform. There were, in fact, two Mulberries, Mulberry A, allocated to the Americans at Omaha Beach, and Mulberry B, allocated to the British at Gold Beach. The differences between them revealed two distinct philosophies shaped by urgency, pressure, and operational style. At Omaha, the carnage of D-Day's first hours demanded rapid improvisation. The American engineering units worked with remarkable speed, laying out roadways, assembling pierheads, and connecting floating causeways in record time. But speed came at a cost. To accelerate deployment, some anchoring patterns were shortened, and a mix of 25-ton and 40-ton whale spans were used in ways that later proved vulnerable in heavy weather. The Americans achieved the first operational pier of the entire invasion, They were landing vehicles via a Mulberry pier by June 11, but the structure would face significant strain under the coming storm. At Gold Beach, by contrast, British planners adhered more closely to the original specifications. They installed full patterns of kite anchors, used consistent span ratings, and matched their pierheads to the expected load of steady supply rather than emergency throughput. Their caution was not hesitation. It was resilience built into the very bones of the structure. These two approaches, one driven by urgency, the other by endurance, would soon be tested by conditions far more merciless than enemy fire. For the men on the ground, Mulberry represented something almost surreal. Soldiers who had fought their way off the beaches turned to see an entire port rising behind them, not captured, not seized, but assembled. Day by day, massive caissons were sunk into position, forming protective walls. Tugs hauled whale spans through choppy water, securing them to pierheads. Beetles bobbed like patient beasts of burden, ready to lift the next segment. To exhausted infantrymen and tank crews, the floating road became a symbol of permanence. It meant that reinforcements would come. It meant that supplies would flow. It meant that this time, unlike 1940, the Allies would not be pushed back into the sea. Even German commanders, reading reports brought in by patrols or captured prisoners, were stunned to learn that the Allies had quite literally brought their own harbors. Albert Speer, Hitler's armaments minister, later remarked that the Mulberry system was one of the most impressive feats of engineering of the entire war, a creation so unexpected that German defenses had not even considered it. Fixed fortifications had been designed to repel landings, but no one had planned for an invasion force capable of carrying its logistical infrastructure across the channel. The moral angle of Mulberry lies in this contrast between destruction and creation. War is often remembered in terms of what is broken, cities shelled, bridges collapsed, ships burned into the sea. But Mulberry represented the opposite impulse. It was construction in the midst of chaos, engineering used not to destroy but to enable, to sustain, to build the foundation for liberation. The floating road was a gesture of defiance against the logic of war itself. Instead of smashing through enemy ports, the Allies built their own. Instead of relying on captured infrastructure, they brought infrastructure with them. It was an assertion that ingenuity could outmaneuver entrenched power, that creativity could undermine tyranny. And for the men who crossed those floating spans, the tank drivers, the truck mechanics, the supply officers, there was a quiet reassurance in the steady iron beneath their treads. Every meter of roadway whispered the same message. You are not alone. The sea has been tamed for you. These angles, logistical, strategic, psychological, and moral, set the stage for the moment when theory would collide with reality. The floating road had been tested in Scotland. It had been drawn on countless blueprints. It had been approved by commanders who understood its necessity. But none of that mattered until it met the violence of war itself. The true test would come not in a workshop or on a quiet bay, but on the storm-lashed coast of Normandy, under fire, under pressure, and under the weight of an entire army depending on its success. The invasion of Normandy began in darkness, carried by wind, tide, and the heartbeat of thousands of engines. On June 6, 1944, Allied forces stormed the beaches from Utah to Sword, facing machine guns, coastal artillery, underwater mines, and obstacles buried beneath the surf. The landings were uneven, catastrophic at Omaha, costly at Juneau, grinding but determined at Gold. Yet by nightfall, a fragile foothold had been carved into France. Behind the infantry and tanks, behind the chaos and the smoke, another operation had already begun, quiet, methodical, and absolutely essential. The Mulberry harbors, conceived in secrecy and built in fragments across Britain, now had to be assembled in a war zone. The floating roads, the Beetle pontoons, the pierheads, and the enormous Phoenix caissons were waiting offshore, held back only by the need to secure enough beachhead for the engineers to begin their work. On June 7, D+1, Major Allan Beckett stepped ashore at Arromanches, the chosen site for Mulberry B. The fighting had moved inland, but the aftermath of battle still lay across the sand. Burned-out landing craft, shell craters filling with tidewater, and the bodies of men who had fallen during the assault. Beckett carried no weapon heavier than a sidearm. His mission was not to seize ground but to transform the coastline into a functioning port. He joined the Royal Engineers and naval construction teams who had already begun the first steps, surveying, marking anchor points, and preparing the shallow waters for the sinking of the first Phoenix caissons. They worked under the constant threat of artillery, aircraft, and shifting seas. Engineers do not often appear in combat reports, yet in those first days, they were as exposed as any infantryman, moving through surf and mud with tools instead of rifles. Far out to sea, convoys of tugs were towing the components of Mulberry toward Normandy. The Phoenix caissons were among the most extraordinary sights of the war, gigantic hollow concrete blocks, some weighing over 6,000 tons, moving slowly across open water like silent gray fortresses. Their speed was barely a walking pace, and many crews had spent days at sea escorting them. As they neared Arromanches, these concrete giants were maneuvered into position with precision that bordered on miraculous. One by one, valves were opened, flooding their internal chambers. The caissons settled onto the seabed, forming an outer breakwater that would shield the harbor from the worst of the channel's aggression. Even before the floating roads arrived, the coastline had begun to change, shaped by human hands into the first contours of a safe landing place. Behind the breakwater came the pierheads, the great steel platforms known as Lobnitz pierheads, which rose and fell with the tide on massive legs. They were designed to interface directly with transport ships and landing craft, allowing cargo to be unloaded regardless of water level. But without the whales, the pierheads were isolated islands. The floating roads would become the arteries that fed them to the shore. Soon, the first spans began arriving, towed in long chains by tugs. They floated like metallic serpents across the waves, guided carefully toward the pierheads where engineers waded waist-deep in surf to connect them. At Omaha Beach, Mulberry A was taking form at astonishing speed. The American engineers worked under relentless pressure, knowing that the devastation of D-Day had left their beach with limited unloading capacity. They laid out pontoons, assembled spans, and anchored them with whatever equipment was available. By June 11, D+5, the Americans achieved what seemed impossible. Their first whale roadway was operational. Vehicles rolled from ship to shore over a floating bridge, bypassing the deadly surf zone entirely. It was the first visible proof that Churchill's idea had become reality. At Arromanches, the British made steady, deliberate progress. They installed full kite anchor patterns, secured the Beetles at exact intervals, and aligned the whale spans with practiced precision. As more and more segments locked into place, the structure took on the appearance of a gleaming ribbon stretching from the pierhead toward the land. Beckett watched the spans flex rhythmically with the incoming tide. Every movement confirmed the integrity of the design. Every thud of a tank tread on steel reinforced the point. The floating road was no longer an experiment. It was a working lifeline. The first tanks and supply vehicles to cross the Whale had no idea of the complexity beneath them. To the drivers, it felt like any other steel road, albeit one that rolled gently like the deck of a ship. But to the engineers standing at the waterline, each successful crossing was a victory measured in inches and seconds. They knew how narrow the margin for error truly was. They had built a port where none existed, and it was holding under the weight of war. Yet even as the Mulberry harbors reached operational status, a force far greater than artillery or sabotage was gathering beyond the horizon. The first clouds rolled in from the west. Winds shifted. Barometers fell. And by June 18th, the channel began to churn in ways no chart could fully predict. The floating road had proven itself in battle. Now it would face the oldest, most merciless enemy of all, the sea. The storm arrived with almost no warning. At first it was only a stiffening wind, the kind that sailors mark with narrowed eyes but not immediate alarm. Then the swells began to rise, slow, heavy, deliberate. By the evening of June 18th, the horizon darkened into a single advancing wall of cloud. The barometric pressure dropped sharply, and those who worked on the Mulberries felt a quiet dread settle over the water. Some had seen channel storms before, but none imagined they were about to face the worst one in 40 years. By dawn on June 19th, the invasion beaches were no longer battlefields. They were the stage for a natural assault far more dangerous than anything the German artillery could deliver. At Omaha Beach, Mulberry A took the first and hardest blow. The harbor's protective line of bombarded floating breakwaters began to twist violently under the rising waves. Anchors dragged. Cables snapped under strain. One by one, the massive steel structures broke free and crashed against the whale roadways with the force of battering rams. The lighter anchoring pattern chosen during its rushed assembly left the American harbor exposed, its components straining beyond operational limits. Engineers watched helplessly as sections of roadway were lifted like toys and slammed back into the surf. Pierheads tore loose, drifting into deeper water before capsizing. Beetles overturned, scattered like broken shells along the storm-fed tide. By the second day of the storm, Mulberry A was no longer functional. The sea had dismantled what men had built in a matter of hours. Efforts to save portions of the structure were heroic but futile. The American commanders made the grim decision to abandon the harbor entirely. What had been a symbol of ingenuity and determination became, under the punishing wind, a graveyard of twisted steel. Its remains washed ashore in jagged fragments, silent testimony to the impossible conditions that had overwhelmed it. The loss was bitter, but the lessons were immediate. The sea cares nothing for urgency or bravery. It yields only to preparation and design. 40 miles east at Arromanches, Mulberry B braced for the same storm. The waves crashed over the outer line of Phoenix caissons, sending spray high into the air. Winds howled across the harbor. Whale spans groaned under the shifting weight of water and machinery. Yet something was different here, something crucial. The British harbor had been assembled methodically, with every kite anchor placed according to Beckett's specifications, every roadway aligned with the precision of a shipwright's craft. As the storm intensified, the whales moved not as rigid beams but as a living chain. They flexed, twisted, and rose with the waves. Their joints absorbed the sea's violence instead of resisting it. The Beetles dipped and lifted, their buoyant rhythm keeping the spans from striking the pierheads with lethal force. The storm raged through June 20th and into the 21st. At the height of its fury, waves reached heights that would have snapped traditional structures clean in two. Engineers on the pierheads reported seasick vertigo as the platforms climbed and fell in dizzying arcs. Some sections of roadway were damaged, a few Beetles were lost. But every hour that passed proved the same truth. The whale design was doing exactly what Beckett intended. It was bending, not breaking. Anchors held fast. Spans stayed connected. Even amidst the worst conditions, the harbor never lost its fundamental integrity. Perhaps the most extraordinary fact of those days was that Mulberry B continued to function, however limited, even at the storm's peak. Ammunition and medical supplies trickled ashore through brief lulls, carried over the floating roads by vehicles whose drivers could scarcely believe what they were crossing. The harbor served not just as infrastructure but as a stabilizing presence, a reminder to the troops on land that despite the storm's fury, the lifeline to Britain remained intact. On June 22nd, the wind finally eased. The sky cleared with the suddenness that only storm breaks can deliver. The surviving engineers emerged onto the battered structures to assess the damage. The scene was harrowing: torn pontoons, twisted metal, scattered debris, but the essential framework of Mulberry B remained. It had endured what the Americans and even some British planners had feared impossible. Beckett himself walked the surviving whale spans, observing each joint and anchor, noting where improvements could be made. He understood, perhaps more deeply than anyone, that the harbor's survival had validated not only an engineering design but an entire philosophy of flexibility over rigidity. In the days that followed, American engineers transferred what equipment they could salvage from Mulberry A to reinforce Mulberry B. The combined effort transformed the British harbor into the central logistical artery for the Allied advance. What began as two harbors would now continue as one, made stronger by experience, shaped by adversity, and proven by the storm that had tried to destroy it. The floating road had survived the sea's ultimate test. Now it would be asked to sustain an army. When the storm finally passed and the full extent of the damage was understood, a stark reality settled over the Allied command. One harbor had been sacrificed, and the other had become indispensable. Mulberry A at Omaha lay in ruins, its shattered remains scattered along the coastline like relics of a broken machine. But Mulberry B, battered, scarred, yet unmistakably alive, became the beating logistical heart of the Normandy campaign. What had been planned as a dual-port operation was now a single-port lifeline, carrying the burden of sustaining the advance of hundreds of thousands of soldiers across France. Engineers worked around the clock to repair damaged spans, replace lost beetles, and strengthen anchor lines weakened by the storm. Their efforts were not merely in service of construction, they were in service of momentum. Every hour the harbor functioned meant fuel for tanks, ammunition for artillery, rations for infantry, and medical supplies for the wounded flowing steadily across the floating roads Beckett had designed. The scale of the operation that Mulberry B supported was immense. In the weeks following the storm, the harbor routinely exceeded its design capacity of 6,000 tons per day. On several days, it surpassed 9,000 tons, a figure that astonished even those who had believed in the project from the beginning. Cargo ships lined up offshore, their hulls brimming with everything an army needed to live and fight. Petrol in jerrycans, crates of rifle ammunition, Bailey Bridge parts, medical tents, spare engines for Shermans and Cromwells, and even prefabricated airfield equipment. Through the Lobnitz pierheads, cranes swung ceaselessly, unloading trucks that then rolled across the floating whales toward the shore. What had once been a quiet fishing village at Arromanches was now the gateway through which the liberation of France was supplied. Mulberry B's value became even clearer as Allied operations expanded. The British and Canadian divisions pressing toward relied heavily on consistent resupply to maintain their offensive. Major operations, Epsom, Charnwood, Goodwood, were fed in part through the artificial harbor. The ability to land vehicles directly onto the beach via the floating roadways meant that reinforcements arrived faster than the Germans expected, often outpacing attempts to fortify or counterattack. Even the American breakout at St. Lo and the thrust toward Avranches benefited indirectly from Mulberry B. Though the U.S. Army increasingly used open beaches and captured ports, the British harbor absorbed enormous logistical strain, allowing the Americans to redirect shipping where it was most needed. Through it all, Allan Beckett continued to serve quietly in his role, advising on the maintenance of the whale roadways and the placement of additional kite anchors. His contributions did not make headlines. He received no field command, no dramatic commendation in the moment. Instead, he worked in the same manner he had always preferred, observing, calculating, refining. He traveled between the pierheads and inland engineering posts, ensuring that every repaired span met the same standards that had allowed the harbor to survive the storm. His expertise proved essential in stabilizing the structure as the tidal conditions shifted through the summer. As autumn approached, the front line moved farther from Normandy, and supply routes shifted to newly liberated ports across France. Mulberry B continued to operate, though at reduced intensity. Even then it served new purposes. Damaged ships were repaired inside its sheltered waters, engineers used its components to bridge rivers and canals, and portions of the whale roadway were repurposed for temporary crossings needed by advancing forces. The harbor had fulfilled its primary mission, but its usefulness was far from over. By the time it was finally decommissioned in late 1944, Mulberry B had landed hundreds of thousands of vehicles, millions of tons of supplies, and uncountable hope onto the shores of France. Its floating roads had carried soldiers to the front and wounded men back toward safety. Its breakwaters had calmed seas that would have otherwise destroyed landing craft. It had bridged not merely distances but the fragile gap between invasion and victory. And even as its components were dismantled or reassigned, the legacy of the floating road was already spreading across Europe, across engineering disciplines, and into the post-war world that would soon emerge from the shadow of war. When the pressure of the Normandy campaign eased and Allied forces pushed deeper into France, Mulberry B did not simply vanish into history. Its components, those same spans, pontoons, and anchors that had defied the worst Channel storm in decades, found new life across a recovering continent. Engineers dismantled sections of the floating roadway and transported them inland, where they were reassembled as makeshift bridges over rivers whose crossings had been destroyed by retreating German forces. In Belgium, whale spans became part of temporary routes supporting the rapid advance toward the Scheldt. In the Netherlands, They helped create essential connections during the liberation of Wigtown and later during the crossing of flooded, war-torn lowlands. Wherever infrastructure had collapsed, Mulberry's pieces stepped in to replace it. What had begun as an invasion tool evolved seamlessly into one of Europe's earliest post-war rebuilding resources. Even after the fighting ended, the ingenuity of the design continued to echo through peacetime engineering. Allied reconstruction offices discovered that whale spans were remarkably adaptable. Their lozenge girder construction made them both strong and relatively light, and their modularity allowed them to be assembled in remote areas without heavy machinery. In the late 1940s and early 1950s, several nations incorporated surplus whales into long-term infrastructure projects. Some were shipped as far as West Africa, where they supported sections of roadway in Cameroon. Others were used in British industrial complexes. At Ford's Dagenham plant, whales were installed as loading ramps to move newly manufactured cars directly onto transport ships, an irony Beckett himself might have appreciated, as his wartime invention found a place in the machinery of peacetime commerce. But while the components scattered, the memory of their inventor remained comparatively quiet. Allan Beckett returned to civilian engineering, applying his knowledge to marine structures, harbor works, hydraulic systems, and coastal defenses. His post-war career was marked by a consistent theme: practical brilliance paired with modesty. He never sought public acclaim for the Mulberry system, nor did he position himself as its heroic creator. Yet among those who worked with him, there was a deep respect for the calm, analytical mind that had solved problems few others could even articulate. He became a trusted figure in the British engineering community, contributing to major projects without fanfare, always focused on precision and purpose rather than recognition. Over time, however, as the historical understanding of D-Day deepened, Beckett's contributions began to receive the acknowledgement they deserved. Museums collected surviving whale spans, restoring them as educational exhibits to convey the scale and audacity of the Mulberry harbors. Visitors at the Imperial War Museum Duxford can stand beside one of these spans and glimpse the blend of simplicity and sophistication that allowed it to survive the storms of 1944. Along the Normandy coast, the concrete ruins of the Phoenix caissons still rest in the surf at Arromanches, forming a silent semicircle visible from the cliffs above. At low tide, the sea retreats just enough for their massive forms to rise from the water like monuments carved from time itself. Between them, one can imagine where the floating road once stretched, alive with the motion of waves beneath and the weight of an army above. In Beckett's home county of Kent, a stained-glass window at Church honors the Mulberry harbour through symbols: a whale roadway, a kite anchor, and the silhouette of a mulberry tree. At Arromanches, a bronze memorial stands not far from where the floating road once touched the shore, offering a quiet tribute to Beckett's role in shaping the course of the war. These memorials do not glorify battle. They commemorate creation, engineering as an act of resolve and hope. By the end of the 20th century, historians increasingly recognized the Mulberry harbors as one of the most ambitious engineering projects ever attempted under combat conditions. They were not perfect, and they were not permanent, but they worked because they were flexible, intelligent, and designed by minds that understood the sea as deeply as they understood steel. The floating road, once a desperate solution to an impossible problem, had become a testament to what human ingenuity can achieve in the face of overwhelming need. Its pieces may have been scattered, but its legacy remained anchored firmly in the story of liberation. History often remembers wars through their moments of violence, the clash of armies, the thunder of artillery, the sacrifice paid in blood. Yet victory is rarely secured by force alone. Sometimes it emerges from the quiet persistence of people whose names never appear on battle maps. The floating road that stretched from the sea to the sands of Normandy was not a weapon, not a fortress, not a piece of strategy forged in a general's headquarters. It was the work of engineers, practical minds confronted with an impossible problem and told to solve it because millions of lives depended on their success. In that sense, Mulberry was more than a harbor. It was the embodiment of a belief that ingenuity could shape destiny. Long after the guns fell silent, the remains of Mulberry B continued to rest in the shallows off Arromanches, half consumed by the tides, half preserved by them. Standing on the cliffs above, one can look down at the broken arc of Phoenix caissons, massive, immovable, yet now softened by time, and imagine the road that once connected them to the shore. Tanks rolled here, trucks rattled here, stretched across these waves by steel spans that rose and fell like the breath of the sea. Beneath their treads lay the vision of a young engineer who understood that the strongest structures were not those that resisted nature but those that worked with it. What Beckett created was a reminder that war, for all its destructiveness, can also inspire acts of profound creativity. His floating road carried more than supplies. It carried confidence, momentum, and the quiet assurance that the Allies could not be turned back. It helped transform a narrow beachhead into a gateway to liberation. And in doing so, it proved that sometimes the most decisive blows of a conflict are delivered not by those who fight at the front, but by those who build the means to sustain the fight. As the tide rises and falls over the remains of Mulberry today, the water moves in the same rhythm that Beckett studied and respected. The sea has reclaimed much of what was once built, but not the meaning behind it. For in the end, the floating road taught a lesson that transcends the war, that resilience, flexibility, and human ingenuity can carry armies across oceans and carry history into a different future.